Let ABC be a triangle with AB equals 10. Let D be a point on the opposite side of line AC as B, so that triangle ACD is directly similar to triangle ABC. Let M be the midpoint of AD. Given that A is the centroid of triangle BCM, compute BC squared. So let's try drawing our diagram. So we have a point A here, and then we can try putting point B and point C here. So it might look something like that. And then we have a point D on the opposite side of line AC as B, so that angle ACD is equal to angle ABC. So it looks something like that, or actually something like this, because this angle and this angle are equal. And then we also have that angle CDA is equal to angle BCA. So it looks something like that. So this is our point D. So that's A, and then this is the midpoint M, and immediately we see that this is not an accurate diagram because A lies outside the triangle BCM. And after a bit of further inspection, we immediately see why it's inaccurate, because we're assuming this angle to be acute, and that makes this angle less than 180, and this puts A outside of the triangle. So instead of this triangle being an acute triangle, we rather need it to be obtuse. So let's let this be A, then B, and then suppose C here. Or let me go ahead and draw that again, so that I'll draw it a bit lower. So A, B, C. And here's our triangle. And then we construct D, and so that this angle is equal to this angle, and then we also have something like that. So there's our point D. And the two triangles are similar. And then we have the midpoint M, and this is the centroid of the triangle. So let's see how we can interpret the centroid condition. So because it's a centroid, we note that the centroid is just the intersection of the medians. So that means that AM bisects BC. So let's go ahead and put that at the midpoint. Actually, we'll call the midpoint P to avoid using the same name. So this angle here, as we discussed, is equal to angle here, and this angle here is equal to 180 minus this angle here. And so this angle here and this angle here add up to 180 degrees. I'll just write it out. And for those of you who are comfortable with this, and a bit of work shows that this implies that AC is the external angle bisector of angle BAP. In other words, it is perpendicular to the normal angle bisector of angle BAP. And furthermore, C lies on the line BP, and these lengths are equal. I've redrawn the diagram here to avoid things becoming a mess later on. So now that we know that CA is the external bisector of angle BAP, and that C lies on BP, we can use something called the external angle bisector theorem, which is very similar to the normal angle bisector theorem that you all know and love. And here's how it goes. So the external angle bisector theorem states that when we have this external bisector, we have BC over CP is equal to BA over AP. And you can immediately recognize that as being similar to the old one, because if we draw point E here, this is also equal to BE over EP. And therefore, both of these points here have the same quantity here. And they form a very special thing called a harmonic bundle. You can see my other video on that. But anyway, let's not get off topic here. Using this external bisector theorem, we end up getting BC over CP. Since P is the midpoint of BC as given, we have that this is 2 is equal to, and BA is equal to 10 over AP. So AP is equal to 5. So let's label that in. So now we just have to deal with the other side lengths. So BA bisects CM, CA bisects BM, that seems a bit complicated. So what other properties do we know of the centroid? Well, we know that the medians and the centroid split each other into a 2-to-1 ratio. So which means that this is a 2-to-1 ratio. And this is also a 2 to, because AM is equal to MD as given. Therefore, we have that PA to AD is equal to 1 to 4, which means that PD is equal to 25 and AD is equal to 20. So I can go ahead and list this as 10 and this as 10. Sorry about the inaccurate diagram, by the way. All right. Now we just have to deal with the rest of the angle conditions. So angle ACD is equal to angle ABC. So this angle here is equal to this angle here. And for those familiar with basic angle chasing, this may remind you of the condition for tangent circles. And what this means is that this circumcircle here is tangent to the side BC. And now it's very clear how to finish. We can use power of a point at the point P, since PC is tangent, and get PC squared is equal to PA times PD is 5 times 25, which is 125. So PC is equal to 5 root 5, and since P is the midpoint of BC, BC is equal to 10 root 5, and BC squared is therefore equal to 100 squared times 5, which is 500. And that is the answer to our problem. Thank you so much for watching this video. Please subscribe if you'd like to see more.